Hi everyone. So now we are going to discuss the another property, another transformation of the independent variable, which is called the time scaling transformation. So we are going to use the same examples which we have used in the earlier transformation for the time shifting. So now the time scaling transformation is going to either compress or stretch the original signal on which the transformation is going to be applied. So it's going to be either the shrinking operation, which is the compression operation, or the expansion operation, which is the stretching operation, depending upon the transformation which we write. So let's take an example, just like we have done before. Let's say that we need to plot a signal x of 2n. So the original signal is already given over here, which is the x of n. So please note that this is your original signal and you are asked to plot the x of 2n. So just like before, we are going to again very quickly check how the signal is going to turn out. So let's say y of n is equal to x of 2n. And now we are going to substitute different values of n and try to plot. So starting from the n is equal to 0, so y of 0. So that is going to give me x of 0. So now if I look over here, the value of signal x at n is equal to 0 is basically 3. So let's write 3 over here. Now at n is equal to 1, we are going to get y of 1, and over here inside the brackets we are going to get 2 multiplied by 1, that is 2. So x of 2. So let's see. The value of signal x at n is equal to 2 is basically 1. So we are going to write over here 1. Let's take one more value. N is equal to 2. So if I take n is equal to 2, it's going to give me y of 2, and inside the brackets now it's 2 multiplied by 2, and that's going to give me x of 4. So if I look over here, the value of signal x at n is equal to 4 is basically 0. So the value is 0. Okay, let's take few negative values as well now. Let's take a value of n is equal to minus 1. If I take n is equal to minus 1, that is going to be y of minus 1. And inside the brackets, I'm going to get x of minus 2. So 2 multiplied by minus 1, because this is n. So x of minus 2 is now the value of signal x at n is equal to minus 2 is basically minus 3. So let's write minus 3 over here. And for n is equal to 1, let's take one more value. N is equal to minus 2. We are going to get y of minus 2 and x of minus 4, which you can see that it's 0. Now, if we plot this particular signal, the transformed signal, which is the time scale transformation now, let's try to plot it. We write over here n, and over here it's x of 2n. That is my y of n. And let's put some values 0, 1, 2, 3, and over here minus 1, minus 2, and minus 3. And let's plot the samples now. So if I plot the samples now, what I can see that y of 0 is basically 3. Okay, so y of 0 is basically 3. Y of 1 is 1. Okay, y of 1 is my 1. And then y of 2 is basically 0. So it's a 0. And y of minus 1 is minus 3. Y of minus 1 is minus 3. And y of minus 2 is basically 0. So if we compare these two signals now, what we can quickly see is, first thing is that this particular scaling multiplying inside by some number has actually compressed my original signal. So this is basically the compression, or you can also call it shrinking if you want to call it. So what has happened? My original signal has shrinked 2 times. So the sample at 3, I have got the sample at 3, but then the sample at 1 is now dropped. Then I have a sample at 2, it's fine. And then I have a sample, no more sample. And then if I look over this side, the sample at minus 1, there is no more sample. That value is dropped, minus 1, the value of 1 is dropped. And then the value of minus 3 is retained. So if you compare these two signals, it's the same signal, but it's now compressed or shrinked twice, and the samples are basically dropped. Now, very quickly, what we are going to do is we are going to just to make things a bit clear, we are going to plot the same transformation for this particular signal. So let's plot x of 2t. Let's suppose this is the signal which I want to plot, and this. Okay, so as I have said that this particular transformation, multiplication inside the multiplication of an independent variable with some number like this inside is going to compress your signal. So I'm going to plot the signal again like this. But now the important bit is what's the duration, what's the range. So now this point 4 is at 2 and this particular point is at now minus 0.5. So essentially what I have done is that I have simply divided 4 with 2 and that's going to give me 2. And over here I have simply divided minus 1 by 2 and that's going to give me minus 0.5. So overall impact of the transformation over here is that the signal is compressed. You can see the signal is shrinked. Originally the signal duration was from minus 1 to 4, but now the signal duration is from minus 0.5 to 2. The overall signal is compressed. Now let's take another example and try to see what happens if we change the scaling operator over here. So let's try to plot, let's say now we are going to plot x of n upon 3. So this is a different transformation now. It's still a scaling, but now the scaling parameter is 1 by 3, not 2 anymore. So let's try to get few more values over here and try to understand. Although it should be understood that this is going to be the inverse of this. If this one is compressing or shrinking, this particular should actually expand or stretch this particular signal. How many units? 3 units. So this should be stretched 3 times if I perform this particular transformation. But what we can do is we can have a mathematical background over here. So again, if I write y of n is equal to x of n upon 3, and let's try a few values. So at n is equal to 0, I'm going to get y is equal to 0, and it's going to be x is equal to 0, and the value is 3. At n is equal to 1, I'm going to get y is equal to 1, and inside the brackets now, that is the important bit, I'm going to get x 1 upon 3. Now please note that since we are dealing with a discrete time signal, we don't have any sample value at 1 upon 3. This is not possible. So obvious answer is that this is 0. The signal is not defined at x1 upon 3. Why? Because the signal value, the discrete time signal is defined at only the integer values of the n. There is no value at 1 upon 3. Similarly, if I try n is equal to 2 and I get y is equal to 2, I'm going to get x2 upon 3, and again it's going to be 0 because it's not a discrete value. At n is equal to 3, I'm going to get y is equal to 3, and finally I'm going to get x3 upon 3, which is x of 1, and the value of signal x at n is equal to 1 is now 2. So I get 2 over here. So if you keep on doing this, what is going to happen that y of 4 is going to be 0, y of 5 is also going to be 0, and when you try submitting n is equal to 6, so you get y of 6, you are going to get x of 6 upon 3, x of 2, and that is defined. So x of 2 is now 1. So now let's try to plot it. Let's try to wrap it up. So we do n over here. We write y of n is equal to x n upon 3 over here. We put some value 0, 1, 2, 3, minus 1, minus 2, minus 3, minus 4, minus 5, minus 6, and probably I'm going to need to extend this. So let's take it a bit further. 4, 5, 6, 7, and so on. So let's try to plot the samples now. So what we can see is y of 0 is basically 3. So the sample is at 3. Y of 1 is 0. Y of 2 is also 0. Y of 3 has a value of 2. So y of 3 has a value of, and then y4 is 0, y5 is 0, and y of 6 has a value of 1. So these two samples are again 0, and y of 6 has a value of 1. Similarly, I can plot these sides as well, and you can verify it later on. This is going to be 1, and then this is going to be at -3. So let's compare the original signal, this one and this one now. So what you can say is that the original signal has been expanded or stretched by 3 units. What do we mean by the 3 units? The sample at 0 is still at 0, but the sample at 1 is now at n is equal to 3. The sample at n is equal to 2 is now at n is equal to 6. The sample at n is equal to -1 is now at n is equal to -3, and the sample at n is equal to -2 is now at n is equal to -6. So this is the expansion or the stretching operation. Now let's do the same for the continuous time case, just to have a complete understanding. So what we are trying to plot is x of t upon 3. So let's plot the function first, signal first. So the signal is going to be like this. So now remember, this is the original signal. The transformation is applied on this particular signal. So when the transformation is applied, this particular transformation is applied. So what is going to happen? It's going to now stretch or expand the signal. So the point 4 is going to be at 12, and -1 is going to be at -3. So again, you can get an idea that this particular point is basically 4 multiplied by 3, and this was -1 multiplied by 3. So you basically multiplied the starting and the ending point with the factor which is written over here. So this is, guys, the time scaling property. And just to generalize the things now, I'm going to write over here. So if you have any irrespective that you have an x of n or x of t. So if the transformation is like this, you have x of alpha n, or you have x of alpha t. So if the parameter alpha is greater than 0, which means you are going to have a 2 over here, or 3 or 4 or 5. That is what I mean by greater than 0. In fact, this shouldn't be like this. I shouldn't have said greater than 0. It should be greater than 1. It should be greater than 1. Yes. If the value of alpha is greater than 1, then what is going to happen? It's going to be the compressor signal. And if the value of alpha is less than 1, which means it's going to be now in fractions, it's going to be 1 upon 3, 2 upon 3, or any value which is less than 1, then it's going to basically stretch your signal. So this is the generalized expressions now. But the idea is very simple. If inside the independent variable is multiplied by a factor greater than 1, it's the compression. And if the factor independent variable is divided by some factor, like over here n upon 3, it's going to expand to stretch your signal. So this is the time scaling property, another very useful property which we are going to explore more in the future clips. Thank you.